It's for everybody to trickle in and then we can get started. Awesome. Looks like we have a good number of folks who have joined. Cora, if you want to go ahead and get started, I think we're okay to get started while folks are still trickling in. And I'm making sure that everybody who asked for the Zoom link has it as well. So it looks like most people have found their way here.
Okay. Yeah. Hi, everyone. My name is Cora. I'm a first-year graduate student at MIT in the physics department. And yeah, today I'll be giving you a tour of my lab. But I'm going to start off I just have a few slides. I'll introduce myself a little bit more and then kind of give an overview of superconducting quantum computing, and then get into a little bit about what I actually do for my research, and then I'll take you on a tour of our lab. Okay. So yeah, hi everyone, I'm Cora, and today I'm going to be showing you around the Engineering Quantum Systems Group lab. I'm a PhD student in the Engineering Quantum Systems Group at MIT. And today I'm just going to give a brief introduction about myself and my journey. How did I get to where I am today? Then because I work in an experimental superconducting quantum computing lab, I'll be giving a brief overview of, what is superconductivity, what is a superconducting qubit, and then I'll talk a little bit about the research that we do in this group and the research that I do, and then I'll take you all on a tour of the lab. So first up, again, my name is Cora. I use she, her pronouns. I'm a first-year PhD student in physics at MIT, and I'm in the Engineering Quantum Systems group. And just maybe a couple fun facts about me. I have 2 cats who I'm very obsessed with. And then also in my free time, I really like to row. It was my sport in high school and undergrad, and now I just do it for fun still, but here's a picture of me rowing when I was in my undergrad. So I'm currently a PhD student in physics at MIT, and I'm doing research in experimental superconducting quantum computing. But I didn't always know that I was going to do this. So how did I get to where I am today? Well, it started off, I really always loved science. Like in middle school, my favorite class was definitely like science. And I guess in middle school, it's more general. You kind of have like science class. And that was my favorite. And I also have some members of my family who are physicists, my grandfather and my uncle. And when I started high school, I realized I really loved math, and I really liked physics because it felt like I could take math and do something useful with it. And kind of throughout high school, I just generally enjoyed those things. And I went to undergrad at Wellesley College. And because I knew that, maybe I wanted to become a physicist someday, I thought maybe I want to go to grad school in physics. So I started taking a lot of physics and math classes. And then I also decided to try to get involved in research, because if you want to go to grad school, you have to do research. So I also wanted to kind of just get a sense if I even like doing research, because that would kind of dictate whether or not I would want to go to grad school down the line. So I got my first research experience at Wellesley, and I was working with some quantum phenomena. I was working with entangled pairs of photons, and then also these things called nitrogen vacancy centers in diamond. So diamond is supposed to have this very regular structure with carbon, but sometimes you can have a place where there's a nitrogen and then a vacancy, so nothing in a spot. And then this NV center has some really cool quantum spin properties, and you can actually manipulate the spin with like electric and magnetic fields, and kind of probe it with light and things like this. So I really enjoyed working in this lab, playing around with these entangled photon pairs and these NV centers, because I really got a sense of how does quantum mechanics work? How does entanglement work? How do, superposition and interference work? So all these things that you've been learning about in Qubit by Qubit, I got to actually play around with those things hands-on in the laboratory, and I really loved it. So after that experience, I was thinking, let's see, I really like quantum phenomena. So maybe I would like condensed matter physics. You all have heard of different phases of matter. You've heard of, liquid, gas, solid, but there's actually lots of other phases of matter too. And a kind of umbrella term for solids and other things like that is condensed matter physics. So I went to Caltech to do a research internship in a condensed matter optics lab. And basically what we were doing was we were taking these crystals and we were blasting them with really high powered lasers to excite them out of equilibrium. And then we used another laser pulse to probe the sample and see what was happening in that very short out of equilibrium time. And we were looking for a phase of matter out of equilibrium. And in retrospect, this experience was really cool, but at the time, I don't think I really appreciated it. And I didn't really have a good time. I think partly because the pressures in the specific group that I was in at Caltech were really high. So I found it to be very stressful. And I also realized that I don't really love working with lasers. So when I came back to Boston, because I went to undergrad in Boston near MIT, I was thinking, okay, I really liked quantum phenomena, and I maybe didn't like condensed matter physics so much. What's the next good thing that I could try? And I actually reached out to the lab that I'm currently in today as an undergrad, and I said, I really like, quantum computing sounds really cool. I really want to work in your group. And I started working here when I was an undergrad. And the reason I picked quantum computing is because it felt like the perfect thing. It's basically harnessing this quantum phenomena that I found really interesting to do something useful. And basically, I guess I did okay because they said that I could stay for my PhD too. So that's how I got to where I am today. And of course, when you're looking back on things in your life trajectory, it's very easy to lay things out in a nice line like this. But in reality, my path wasn't so clear-cut along the way, and there's a lot of details that are missing here, obviously. So maybe just to give you all a sense of what my journey has been like in a less glamorous sense, things have not always been perfect for me. So for instance, in high school, for some reason, I'm not even sure why, but I had my sights set on like my dream college. and I did not get in. And I really thought that my life was over and that everything I worked for was a waste because I didn't get into the school of my dreams. And spoiler alert, everything worked out great in the end. I actually had a fantastic experience at the college that I went to, and I think it set me up really well for both being able to do physics research and enjoy it, and then also kind of develop my confidence as a physicist towards going to grad school. So I think it really worked out well, and I probably would have had a worse time at the college that I thought was my dream school at 17. Another thing is I used to be terrified of public speaking and talking about science, and I still am a little bit. I was always just really worried, and I had a lot of self-doubt surrounding the fact that I didn't know everything, and I didn't feel confident, or I was worried that people would judge me. And I will say practice doesn't make perfect, but it does make it easier. So I really had to push myself out of my comfort zone and practice giving talks at conferences, giving poster presentations, things like this. And some good stuff has come, a lot of good stuff has come out of it, but also I discovered that I love teaching. And if I just like stuck with the narrative that, you know, I can't talk about science, I suck at public speaking, then I may not have discovered that and gotten involved with something like Qubit by Qubit. And then another thing is imposter syndrome. And I feel like I've been dealing with this all along the way, and I'm still struggling with this, but I'm working on being more confident in myself and my abilities, and also feeling like it's okay to be learning and making mistakes. And in fact, more than okay, because you can't learn without like having some failures along the way. And also when you go outside of your comfort zone, you're going to be learning and trying new things, and you're going to make mistakes, and that's how you get better. Yeah, so hopefully that just gives you a sense of, you know, who I am, what my journey has looked like, and all that jazz. Now I'll give a brief overview of superconducting quantum computing. So I work in an experimental superconducting quantum computing lab, and that means I work with superconducting qubits. And you learned about some different hardware options in lecture, I think, last week. And you may have heard about trapped ions, neutral atoms. So this is just one possible way to build a quantum computer. But first things first, what is superconductivity? So superconductivity is when current can flow in a metal without dissipating any energy. And it's a really interesting phenomena and kind of complicated too. So I can't really explain to you fully how it works, but I think I can kind of motivate it. So basically when you have a solid, like a piece of metal, and it has all these atoms, which are represented by these blue dots, and the atoms kind of interact with each other. They're kind of like on springs connected to each other. And the atoms at a normal room temperature or high temperature, they bounce around a lot, and these springs are moving. There's a lot of energy. Things are moving around. And then we can also have the electrons kind of freely hopping around and moving through the metal. Then if we take this metal and we cool it down to really low temperatures, the springs get really rigid, and the ions don't want to move around a lot. And then what happens is when you have an electron moving, it kind of slightly attracts the ions in the metal, and then that can attract another electron. And then these two electrons travel together as a Cooper pair, because the deformation in the lattice kind of drags the second electron with it. So in this really low temperature regime, the atoms or ions don't move around that much, and then the electrons pair up with each other and they move around without any energy loss. So this is basically the phenomena of superconductivity, and it also explains why our superconducting qubits, superconducting quantum computers, need to be in dilution refrigerators, because we need our device to be really cold so that the metal is superconducting. So what is a superconducting qubit? You may or may not have seen this before, but there's a very famous circuit called an LC circuit, and L is for inductor. I'm not sure why the letter L stands for inductor, but it just does. And C is for capacitor. So it's just a circuit with a capacitor and an inductor. And these are just two circuit elements. A capacitor is like a piece of metal with a little gap in it. And then an inductor is a little bit more complicated, but it's basically like kind of like a coil, you can think of it. And what happens with this circuit is current oscillates back and forth. So it oscillates over to the capacitor, and charge gets stored up on the capacitor, and then it discharges and flows back through the inductor and charges up on the other side. So this is an oscillating circuit. Current is just oscillating back and forth. And what we want to do is basically think about how we can turn this type of thing into a qubit. And in practice, what we do is we switch out the inductor with a thing called a Josephson junction. And a Josephson junction is basically a superconducting version of an inductor. And it has some nonlinear properties. So it's kind of like a strange inductor. And Josephson junction is actually pretty simple. It's basically just, we have our superconducting material, and then we put a little bit of an insulator in between, and then the superconductor again. And what happens is the Cooper pairs, these pairs of electrons in the superconducting material, they can actually tunnel through the insulating material. And this has like a very interesting nonlinear effect, and that's what we're leveraging here. So what ends up happening is, and we don't need to worry too much about what's going on in this picture, but with the LC circuit, there's different energy levels depending on, you know, how much energy is oscillating in the circuit. And every energy level is evenly spaced. So we have like a 0 state, a 1 state, a 2 state, so on and so forth. And when we switch out the inductor with a Josephson junction, the nonlinearity actually bends the energy spectrum down and makes the spacing between the energy levels different than each other. And that allows us to just isolate the bottom two energy levels and use that as our qubit. So when anyone talks about superconducting quantum computing or superconducting qubits, this is basically what they're talking about. They're talking about a little circuit which has current oscillating in it, which we're using the lowest two energy levels as our qubit. So there's all kinds of qubits. So this qubit here is called a transmon qubit, but there's also all kinds of other interesting qubits. And I'm showing kind of a crazy diagram here, but you can also make qubits called like a fluxonium. And then you get these other strange energy spectrums that you can use. So there's also a lot of research into how can we build different types of qubits out of different types of circuits, basically. But this is the simplest one. So if we have two qubits, we want them to be able to like communicate with each other and exchange energy. So the way that we do that practically is we just connect them with a capacitor. And again, all a capacitor is a piece of metal, basically with a gap. And this is how the qubits can kind of interact with each other and exchange energy. So here's what a superconducting quantum computer can look like. This is a 3D rendering of the device that I work with. And basically it's this thing with two layers, and just to give you a sense of scale, this scale bar here is 1 millimeter. The bottom layer is like 5 millimeters by 5 millimeters, and the top one is like 4 by 4 millimeters. And basically what's going on here is on this top layer, we have all of our qubits, and I'll just zoom in here. And the qubits are these maroon things here. And these are actually the capacitors. So the capacitor in the, we basically have a capacitor and a Josephson junction. And the capacitor is what you see here. And the Josephson junction is super tiny. So you actually can't see it from this picture. And then on the other layer of the chip, we have all the other elements of the quantum computer. So these orange things are the resonators. This is basically how we talk to the qubit and kind of find out what state it's in. And then we also have flux lines. So this is so we can manipulate the qubit with magnetic fields. And we also have this purple and yellow is for interfacing with the readout resonators and driving the qubits or reading out their states. So now I'll talk a little bit about what we actually do in our lab. So first things first, it takes so many people in order to do experiments like we do in our group. And I just want to point out like the whole team here. So we have the Engineering Quantum Systems group at MIT. And then we also have at MIT Lincoln Labs, which is basically a national lab type situation nearby. We have the superconducting qubits team. And MIT Lincoln Labs actually fabricates our devices. So all these things are made at MIT Lincoln Labs. And then we do experiments with them. Just to point out, I'm right here. I unfortunately didn't make it to the picture day, but oh yeah, and then we also have a ton of sponsors. So it takes a lot of people and also a lot of money to do these kinds of experiments. Each quantum computer needs to be in a dilution refrigerator, and all of the dilution refrigerator and all of the electronics that we need, it's like upwards of $1 million per setup. So it takes a ton of money. The great thing is that a lot of people are really invested in this. So a lot of governmental agencies and also companies are like giving us money in order to do these kinds of experiments. And so a really exciting recent development in our lab is we're building up a new lab space now. So I'm going to show you our original lab space because it's right next door. And then I'll walk you over to our new labs, which are really beautiful. So the kinds of research projects that we do in the group, we want to engineer, there's lots of people in the group, different people are doing different things. So these are like, different people are working on different projects. So the types of projects we have some people engineering better qubits. So we're looking at new circuit designs so you can engineer certain properties, also using different kinds of materials to make our qubits, engineering better connections between qubits. So that can be things like long-range connectivity. It's really easy to connect two qubits that are close to each other, but what if you want to connect two qubits that are far apart? Or what if you even have two different chips and you want them to be able to talk to each other? Then you need to build up kind of a quantum network and these quantum interconnects. So some people are working on that. We're also working at developing better gates with higher fidelity, investigating noise processes. So we actually don't understand a lot about noise, where it comes from, how to mitigate it. So working on gaining a better understanding of that. There's some people working on quantum error correction. So basically sometimes things go wrong with your qubits due to noise or other things, and your state changes, and you want to be able to detect that an error happened and fix it. So people are looking at how they can accomplish this both with photons and with using several qubits to encode one logical qubit. And then there's also quantum simulation, so simulating condensed matter physics and complex quantum phenomena on large arrays of qubits. And lots of other things too. There's probably many other projects that I've left off of here. And I work on quantum simulation. So let me just give you a bit of a motivation for quantum simulation. So let's say we want to simulate a system of electrons or atoms or something like this, and we want to know how they evolve with time. Well, we know that an electron actually kind of acts like a qubit, and we've seen before that a qubit kind of has two bits associated with it, 0 or 1. And we can also think about a system with more than one thing. So if we were to have 2 qubits, and this is something we've seen before, then we no longer just have 0 or 1, but now we could be in the state 0, 0, 0, 1, 1, 0, or 1, 1. So our kind of the dimension of the space that we're working in went from 2 to now 4. And in general, if we have n or electrons or atoms that we want to simulate, that's kind of like 2 to the n different options. And this gets really big really fast. So for instance, if you wanted to simulate a collection of 80 atoms, like 2 to the 80 is like that amount of information cannot be stored on any supercomputer on Earth. Like there's no, the exponential scaling just makes it impossible. But the really nice thing about a quantum computer is that it naturally has this same kind of exponential scaling already built into it. And of course, I'm being overly simplistic here because we could simulate more complicated things like molecules or other things that have more than 2 energy levels, in which case a qubit is not a good comparison, but there's still some sort of matching in the scaling of the complex quantum systems and the quantum computer. So basically, quantum simulation is really hard or could be impossible for a normal computer. And what we want to do with our quantum computer is we want to take a complex quantum system of interest. So this could be some condensed matter system, some like we could be looking at some strange phase of matter or something like that. And we map that to our quantum computer. We let it evolve with time, and then we perform a measurement. And by measuring, we learn something about the system of interest that we couldn't study directly. So the 16-qubit device that I work with naturally emulates the hardcore Bose-Hubbard model. And that's kind of just jargon, but the hardcore Bose-Hubbard model is a really good model for something like electrons in a metal. And basically what's happening here is each site can house an excitation. So every site could have some like a particle at it. And then the particles can hop around to anywhere that's open. They can't hop to somewhere that already has an excitation. So that's all the hardcore Bose-Hubbard model is. This is kind of the natural system that the 16-qubit device emulates. But we can also play lots of tricks to emulate other systems. And some other things that we can do, and we have done, is study how entanglement scales on different subsets of the device. So we can entangle the qubits together and see how that scales. We can also generate synthetic magnetic fields by basically modulating or making the qubits' energies oscillate. You can make synthetic magnetic fields. And then we can also see quantum phase transitions. So we can set the, we can prepare the qubit in some condensed matter phase and then change a parameter such that we see the phase change to a different phase. And these phase transitions are really interesting to condensed matter physicists. Okay, so that's all I had prepared, just to give you a sense of what it is that I do. And now I'd love to take you all on a lab tour. So I'm just gonna walk next door.
Cora, while you're walking, do you think you might have time to answer a question or two from the Q&A, or are you close?
Oh, I'm already at the lab. But
okay, never mind. We can save that for later. Keep those questions coming though, folks.
Okay, so it's really loud in here, so hopefully you can still hear me. I'll try to talk loud too. I don't know if you can hear that sound that's going on in the background, but that's the pulse tube, because our qubits not only have to be cold, they also have to be under vacuum. And so this pulse tube is making the vacuum system work. So okay. So I'm in our kind of original lab, the old lab, because now we have a new lab. And we have 4 dilution refrigerators in here. So we have the red one, the blue one, and then the 2 white ones over here. And each of these is currently cold. And we cool the devices down to like about 10 millikelvin. So just to give you a sense of scale, that's like 100 times colder than outer space. And that's how cold we need it to be, both for the superconducting elements in the devices to be superconducting, and also so that the amount of noise is as little as possible. When I was showing you how superconductivity kind of works in like a hand wavy way, I said that as things get colder, the ions in metals like are less vibrating, they move around less because there's less energy. And we basically want to minimize any type of thermal excitations or like extra energy floating around. That's why it has to be super cold. So this is actually not the most interesting thing, because all of these fridges are currently closed. So we can't see any of the quantum computers. But the quantum computers are inside each of these fridges. The fridge is like warmest at the top, and it gets colder as you go down to the bottom. And the chips are at the bottom of the fridge. And when I take you over to the new labs, we'll actually get to see what the dilution refrigerator looks like on the inside. And some of these fridges actually have more than one quantum computer in them. So maybe I'll just show you this one over here. The device that I work with is currently cold inside this fridge right here. Let's see, some other interesting things I can show you. This is the kind of valve diagram for the dilution refrigerator and vacuum system. So you can actually see everywhere where the light is blue, that valve is open. So you can see that right now we have helium, liquid helium, flowing around in the dilution unit. The liquid helium is pretty cold. It's like 3 Kelvin. And then the refrigerator does some like crazy thermodynamics tricks to get even colder and get down to 10 millikelvin. But we get that initial coldness from the liquid helium. And we can see that the liquid helium is flowing around in this path here. And one interesting thing that I'll point out here is if you look here, there's this thing called a trap. And that's actually these cans down on the floor. So these
there's oops, you can see there's a dewar there, and that dewar is filled with liquid nitrogen, and you have like a tube going in and out, and basically what's happening in there is that liquid nitrogen is pretty cold, but not as cold as liquid helium. So basically sometimes you can get particles inside of the dilution unit, and we want it to be under vacuum, but in practice it doesn't always work out perfectly, and we can get some air or whatever random gunk in our dilution unit, and a trap's job is to catch those particles and keep them there. So basically the when stuff passes through and goes into the liquid nitrogen trap, it gets cold and then it gets stuck there and it can't move anymore. Let's see. There was something else I wanted to say, but now I can't remember. Okay. So now I think, unless there's any specific questions about this room, I'll take you upstairs. So we see all the fridges here are kind of dangling from the ceiling, and we need to have all these different lines to connect to the qubit and basically control the qubit with electric and magnetic fields. And so all those lines are actually going straight up through the ceiling into a lab in the room directly above us. And so that's where I'm going to take you all next, so we can look at the control electronics. Okay, I have to go in the stairwell, and the internet connection might be spotty.
Cora, we lost you at the perfect moment. You were like, the internet connection might be spotty, and then you got out. That's totally fine. Keep those questions coming, folks. Cora, if you are able to answer this question on the go, I saw a question that I was also curious about. She might be frozen, so I'll give her a second. Someone's wondering what gas is used in the dilution refrigerator to cool down the quantum computer.
Yeah, so we use liquid helium. And that gets us down to like a couple Kelvin. And then basically in the same way that your refrigerator in your house is colder than like the ambient air in your house, that's kind of a thermodynamic trick that you can do to kind of pump yourself down to colder temperatures. And that exact same type of process is how the dilution refrigerator gets even colder than the liquid helium. So, Junyoung, would you mind saying hi?
Sure. Do I have to say hi here?
Oh, this is a qubit by qubit lab tour.
Oh, okay.
So, Junyoung is one of my lab mates.
Hi, nice to meet you. I'm Junyoung, and I'm a fourth-year graduate student at this group.
Yeah, maybe do you want to just tell them, like, in a sentence or two, what kind of research you do?
Yeah, the research I'm doing is designing and measuring a superconducting qubit with high performance, which high performance means it should have a longer lifetime or improved controllability, so you can more effectively control. And the reason why it is important is one major problem or obstacle that we have to overcome in a superconducting qubit architecture is the lifetime of the circuit is too short. It's like order of like a millisecond only, or hundreds of microseconds. So that's why I'm working on improving and trying to design and measure high performance superconducting qubit.
Thank you, Junyoung.
Yeah, you're welcome, Cora.
Okay. So now we're in the room directly above where we were before. And you can see all these racks with tons of electronics on them. And then there's actually 4 racks. So there's like these 2 are paired together. And then like those two, and then the 2 at the end. And each of these pairs goes to the fridge that's directly underneath it. So I'm actually at the fridge that the device that I work with is in is called Blue Force 1. So I'm at the Blue Force 1 racks right now. And basically all of this the electronics is for controlling the device. And then we can see actually down on the floor here, that little like circly thing that has all the wires connected to it and going down into it, that's going directly down into the fridge. So maybe I'll just point out some of the things that we can see here. The types of electronics that we have like arbitrary waveform generators, so we can generate arbitrary pulse shapes or like oscillating things. We have microwave generators, so we can make provide microwave signals to the qubits. So all the qubits are at the frequency that we need to communicate with them is about 5 gigahertz. So that's in the microwave range. And then we also have some like DC control electronics, so we can apply static magnetic fields or also magnetic field pulses to the qubits. Yeah, so yeah, and this fridge has 2 quantum computers in it. So there's the one that I showed you a 3D rendering of, and then there's also another one that has fluxonium qubits, I think. Actually, I'm not 100% sure, but that's like that crazy circuit that I showed you earlier. So now I think the most interesting thing for us to do is go over to the new lab. The new lab is really beautiful, and you can actually see the insides of the fridges because all of the fridges are warm and they're open. So we can go check that out right now. And hopefully the internet connection will be good as I walk there. But we'll see. And it's a bit of a walk. It's going to be like a 5-minute walk. So I would be happy to take some questions as I'm walking over there.
Do you think it would be helpful if I read those questions to you, Cora?
Yes, that would be very helpful.
Awesome. Let's take a look. Okay. Let's see. I'm trying to get some specific questions to the lab that you just showed us. Okay, here's an interesting question. We have somebody wondering, like, can you have a quantum computer where there's no refrigeration system involved? Like, does that exist?
Yeah, that's a really good question. As far as superconducting qubits go, that is not possible at the moment because we don't know of any materials that are superconducting at warm temperatures. We only know of superconductors at really cold temperatures. But actually, this is a big search in condensed matter physics. People are looking for high TC, high critical temperature superconductor. So you saw that I showed you when you go below a certain temperature threshold, this generation of Cooper pairs, the electrons pairing up with each other, starts to happen. And we would really love to find a material that does this at a relatively high temperature, because then we could have electrical currents running without losing any energy. And this would be kind of a gateway to like a green energy future. As far as other hardware platforms go, I'm pretty sure they also
need to be cold because we don't want any thermal excitations. Basically, when things are warm, there's a lot of extra energy floating around, and this just makes more of a noisy environment for our qubits and impacts things like coherence times. So we know it's really important to keep track of the phase information for our qubits. And that is going to be lost when it's very noisy. And then also because we're working with like a ground and a first excited state of a qubit, we don't, and there's also like more higher energy levels. We don't want to accidentally go to higher energy levels that we don't intend to. And we also don't want to like be forced to decay down to the ground state really quickly either.
Amazing. And I have a question that kind of relates to that. We have somebody wondering how much energy is used to cool and maintain those temperatures, if you know. Looks like we might have lost Cora for a second, but we'll just give her a second. I'm sure she'll be back. No worries, everyone. Just hold tight. I'm seeing your reactions. You guys are funny. Feel free to keep those questions coming into the Q&A as well while we wait for Cora to reconnect. I just turned on the chat for a second. If you want to go ahead and say hello in the chat, and then you can also say your favorite part of the tour so far. I think Cora might have to reconnect, but feel free to pop into the chat while we wait. Yeah, of course, Charles. We're just excited that you guys are having a good time. It's great to see how much you guys are enjoying this. I'll always love to see that. I can't wait to see the new lab. We'll just have to be patient while Cora reconnects. Yeah, I totally agree, Rishi. The electronics involved in the lab are super cool. Hey, Cora.
Wait, sorry, I lost the internet connection.
No worries at all. We just had some folks coming in the chat saying their favorite part of the tour so far, and it looks like everyone's really enjoying it. So,
okay, can you make me a co-host again so I can share my video?
Definitely. All right, you should be good to go.
Okay. If you thought the other lab was cool, just hold your horses. So now I'm in the new lab, and this lab is already a million times better than the other lab because it has windows, so you can have sunlight and it's not just a concrete dungeon. So that's a huge advantage. And then actually the inside of here is way more pretty too. So here is 2 of our new fridges. So here's one, and now you can actually see what it looks like on the inside. We have all these like we have all these different layers, and it gets colder as you go down to the bottom. And then the very coldest part is at the bottom here. And these are called this is called like a cold finger, and it kind of comes down. And this is where we would attach our quantum computers to. So I can show you also, and actually I lied. One of the fridges is closed and I think being cooled down right now. But that's a new development because I'm pretty sure it was open yesterday. And here's another one. And this one is the same as the other one basically. Now you can see like two cold fingers here and here. And actually both of these fridges are relatively small. The two ones I just showed you over here. And this is
No worries, y'all. I see your reactions. Y'all are funny. It's okay. We'll just wait for her to reconnect. I know she'll be back soon. I think you're muted, Cora, but we can see you now.
Oh yeah. I think that the internet connection is not the best here. But these fridges I'm really excited about because they have high density wiring. So that means we can have a ton of lines going down into the fridge. And that enables us to have more qubits in a quantum computer. So here is one of our big fridges. And then the other one over there actually is getting cold right now. But you can also see here all these different cans. And this helps us kind of understand what's going on with the cylinders. It's not just one big cylinder on the outside. It's actually like a Russian nesting doll of different layers that provide both thermal insulation and also radiation shielding. And then actually, I'm going to try and sneak in here because so I can show you all the high density wiring because I think it's actually really beautiful. Wait, it's so hard to see. Yeah. But okay. So I think I've gone a little bit long on the tour side of things, and I want to make sure that there's time for questions. And of course, if you have any specific questions about things from this lab, I can still like go back and show you, but maybe I'll just sit here for a second and answer some questions. And then I'll also point out that there are racks here for all the control electronics, but you can see a lot of it is still empty. We haven't finished filling them out and putting this stuff into them yet. So yeah, this is our new lab, just getting started. Very exciting.
Yeah, and I think the best place for questions is in the Q&A, and just feel free to pick whichever questions stand out to you that you want to answer.
Okay, I actually oh, do you have to have any special precautions when working with the refrigerators? Like, do you deal with radioactivity things and things like that? Not really. The only dangerous thing is the damage that we could cause to the fridge. So like when we're dealing with anything on the inside of the fridge or, opening and closing it, we always wear gloves and we have to be careful to keep things nice and clean. Yeah, we don't want any dirt or oils from your fingers or anything like that could disrupt the potential for a vacuum seal. How many qubits are in one computer? And how did you determine the 5 gigahertz frequency to interact with the qubits? Great question. So the number of qubits in a computer can vary. So the one that I work with has 16. We also have another device with 9, and then we have a lot of devices with like less than that. So we have a lot that have like only a couple. And in the past, we've kind of been limited by the number of lines that go into the fridge. So the fridges that I showed you in the other lab do not have that many lines. And these 2 big fridges that I just showed you actually have way more lines, so we can have way more qubits. And yeah, that high density wiring is what enables us to be able to do that. Those really pretty wires. And those are insanely expensive, actually. The cost of everything in this lab is actually obscene. Yeah, and then another thing that's cool is, I don't know if you noticed, but the wires are kind of like bendy. Sometimes you see quantum computers, and the wires have like a loop or like a bend in them or something like this. And the reason for that is that when you thermal cycle the wires, they can kind of expand or contract a little bit. And if the wires were just straight and rigid, they might snap. So this just gives them a little wiggle room to expand and contract. Okay, and then 5 gigahertz. Okay, so this is coming from basically the circuit design. So I showed you that is basically like an LC circuit, and depending on how you choose the inductive and capacitant energies, you can control the frequency of the qubit. And the frequency of the qubit is the frequency that you communicate with it at. And yeah, I think 5 gigahertz approximately is very convenient, because that is in like the microwave range. So how many max quantum systems can be mounted on these fridges? So that's a great question, and it really depends on how many lines you need. So for instance, if you only need a few lines, you could have a bunch of quantum computers. But if you have one really big computer with a ton of qubits and you need a ton of lines, then you're not going to be able to have that many. Maybe just one. How do they come up with the design of quantum computer? Like, why is it having wires and levels? So the quantum computer itself just sits at the very bottom of the dilution refrigerator. And I think you're talking about the levels of the dilution refrigerator. I actually, the dilution refrigerator design definitely was like a great work of thermodynamic engineering. And I am no expert in that. So I don't have a sense of like how they came up with that. And then all the wires, each qubit, we need to communicate with it, and we need to manipulate it with electric and magnetic fields. So basically, for every qubit, we have to have at least one line to communicate with it directly. And then we also have to have lines connected to the resonators. And we can do a kind of a sneaky thing. If the qubits are at different frequencies, we can actually talk to all of them at once by doing this kind of frequency multiplexing, because the different frequencies don't really interact with each other. And that's how you can have up to like 8-ish qubits with one per cell filter and feed line. So basically you need like on the order of 1 line per qubit plus 1 per every 8 qubits. Okay, what is the difference in efficiency and capacity between the old lab and the new one? So they both have 4 fridges. The fridges here are newer and nicer. And also the 2 ones are much bigger, so we can have bigger devices in the future. And then the other ones, yeah, I'm not sure. We haven't actually done anything with this new lab here. We've just been building it up for the past 6 months. So there's been no output from the new lab yet, but there will be in the future. And the other nice thing about this is now we don't have to share as much, because there's been a lot of waiting time where a grad student or a postdoc really wants to do an experiment, but there's no fridge space to do that. So now we're going to have a lot more fridges, and more people are going to be able to do experiments at the same time. maximum number of qubits on a processor currently being used. In our lab, 16. At Google, I think they just made like 1,000 something qubit processor. So the goals of industry and academia are different. So Google uses, or IBM or all these big companies, they use tried and true methods and designs. So they use the transmon qubit because they know it works really well. It's reliable, and they basically everything is just, you know, tried and true, and they're trying to scale up and make it bigger and bigger because they want to say, okay, we want to make we want to have a quantum advantage. We want a useful quantum computer. You know, we want 1 million qubits, whatever their grand vision is. In academia, we can be a little bit more creative. We have more freedom to be like, okay, I want to try a new material. I want to try to engineer something better rather than just using what's already been made and making it bigger, basically. So that's kind of the difference here. Is the setup sensitive to external vibrations? Yes, it definitely is. Like if you bump the fridge, you could cause problems. And we also have issues with noise in our devices. And basically there can be weird stuff in the substrate that interacts with your qubits in ways that you don't want it to. And we call these like defects or whatever that couple to your qubits and kind of tank their coherence times. And if you bump the fridge, you can actually like shift around and cause weird things to happen, and maybe induce these defects or move them around. Okay. How many operations are computed every second with the specific devices that we have at MIT? Oh, this is an interesting question. I don't know. Every quantum gate that we do takes about 40 nanoseconds. So if we were like maximizing what we could do, every gate would take 40 nanoseconds, and then we need about 1 microsecond every time we want to read out the qubit state. In practice, we're not just like continuously running experiments all the time, but yeah, 40 nanoseconds per gate, and then 1 microsecond approximately every time you want to read out the state of your qubit or qubits. Yeah, so the refrigerator, do the refrigerators already contain liquid helium, or do specific technicians add it? So we actually have all these like these giant dewars sitting around. Maybe you saw them in the other lab too, but those are filled with either liquid nitrogen or liquid helium. And each dilution refrigerator has a store of liquid helium, and ideally you should never lose any helium. It should always be staying in there because you just like cycle it through, and you should never be losing any. So in theory it should just, you know, last a long time, but in practice we may have to add a little bit of helium every now and then. Okay. So someone is asking about Q-trits. So if you remember, I showed you the energy level diagram of the transmon qubit, and it was kind of you know, 0 and 1 were the furthest apart, and then 1 and 2 were a little closer, 2 and 3 were a little closer. So if you want to use a transmon qubit as a Q-trit, you certainly can, but now you just have to pay attention to the frequencies between the different levels, and that's the frequencies that you need to communicate at. So before, when I said, you know, qubit is 5 gigahertz, that's the energy difference is associated with a frequency, and that frequency is 5 gigahertz. But then for like 1 to 2, it's going to be 5 gigahertz minus like 200 megahertz. So like 4.8 gigahertz. So then if you want to do Q-trit stuff, all you have to do is just pay attention to what frequency your communicating with the qubit at and what level your qubit is at. So if you're at 1 and you want to go up to the 2 state, you need to communicate at the right frequency to go from 1 to 2. And I actually do Qtrit stuff. One of the experiments that I'm working on is this like double on hopping. And basically when you have when you go from 0 to 1, it's like you have 1 excitation at that qubit. And if you go from 1 to 2, now you have 2 excitations. And if you have a square with 4 qubits and you prepare 2 excitations on one corner, you can see how those excitations walk around in the square of qubits. So that's an experiment that I'm working on. Okay. One of the doers is just like blasting out gas. They do that occasionally. Oh, it scares me so much every time. Okay. There's a lot of questions and we don't have a lot of time. I'm trying to think what's how are quantum gates physically applied on these qubits to change their state? This is a really great question. And basically the qubit has an inherent frequency. Is kind of its natural oscillation frequency. And when I say oscillation frequency, I mean the oscillation between the 0 and the 1 state. Okay, no, I take that back. When I say the qubit's natural frequency, I mean that if you were to take the qubit and put it on the equator of the Bloch sphere, we usually think of that vector as being static, but in reality, it's actually precessing, rotating around at the qubit's natural frequency. And this is kind of like a spin in a magnetic field. And the really cool thing about a spin in a magnetic field is if you drive it with an electric and magnetic field that oscillate at that same frequency, that's the natural spin frequency, then you can actually induce these oscillations and you drive it from the 0 to the 1 state back and forth. And exactly how this works out is a little bit complicated, but you can just take my word for it right now that if you drive with an electric magnetic field at the correct frequency, you can drive the qubit from the 0 to the 1 state. So then if you're in the 0 state and you start driving at the right frequency, your qubit is gonna, or if we think on the Bloch sphere, is gonna go around and around like this. And basically, if you want to do a pi pulse, so you want to go from 0 to 1, you just need to have your gate be the right amount of time for you to go from 0 to 1. Or conversely, you can change the amplitude of the microwave pulse that you're giving. And this will also and keep the time fixed. So usually we keep the time fixed at 40 nanoseconds and we sweep the amplitude of the driving field, the microwave pulse, and that changes, or basically if you do the right amplitude, you can apply a pi pulse or a pi over 2 pulse or whatever. Okay. What is your advice for undergrad first year who want to be involved in quantum computing, AI, and astrophysics? My advice would be talk to faculty members. So if you at least at start with your home institution, just go online, look at what all the faculty members do, what their research are, and if it's interesting to you, ask them, hey, can I have a chat with you? I'm really curious about your research. Most professors love to tell you about their research. They're super passionate about it. It's their life's work, and they love talking about it. So if you send an email and you're very genuine, and you say, I'd love to just, learn more about what it is that you do. I see it looks super cool. They'd probably be willing to chat with you. That's actually how I got 2 out of my 3 research experiences in undergrad, is I just emailed the professor and I was like, oh, I really like what you do. Can I chat with you and maybe talk about possibilities to get involved. And then that led to, oh, you know, here's more about what I do. And actually I have this project going on with this. Would you want to work on it? So yeah, just talk to people. I went to a school with no graduate students. It was undergrads only. So that wasn't really a resource available to me, but also you can talk to grad students too. And that's a really great resource. Grad students who do stuff that you're interested in. Yeah. Okay. How does entanglement happen inside of a quantum computer? So basically what can happen is I showed you before that the qubits are connected via a capacitor, which is basically just a piece of metal with a gap in it. And what we can do is we basically prepare one qubit in an excited state. So we put it into the one state, and then we let the two qubits like communicate with each other and share energy between the two of them. And that's how they can become entangled with each other. They have to share energy with each other. Are there certain types of qubits that are better for running certain quantum many-body quantum simulations? Great question. And yes, for sure, because the types of systems that you can simulate depends on the so basically you want to engineer the energy landscape of your device to look like the energy landscape of the system that you want to simulate. And different qubits have these different types of energy levels and energy spectra. And depending on what you're looking for, you may want different things. So off the top of my head, I don't know of a good example. Oh yeah, one thing you could do is, and some people are interested in this in my group, is we can do a lot of fermionic simulations, because in the limit that we're working in, we really only have one excitation or 0 excitations at each qubit, because we truncate to just the ground and first excited state. Of course, I talked about how you can intentionally go to the second excited state if you want to, and that's a whole other thing. But you could also think about, what if you had a way to have bosonic modes also in your quantum computer, and you kind of have qubits, which are kind of fermionic, and also some cavities or something with photons that have these bosonic modes. So more like actually just an LC circuit rather than a qubit. And then you can do some like combo bosonic fermionic simulations. Okay, what would be your advice if there's no professor doing research on quantum computing at your home institution? I would highly recommend applying for REUs and other types of outside things if you're an undergrad. I'm not sure what kinds of opportunities there are as a high schooler, but at least for undergrad, if you don't have the opportunities at your home institution, you should apply to go to other places too. But then I will also say that just because you don't have access to it at your home institution does not mean that you can't apply for it for grad school. Basically, when they're doing grad school admissions, they're looking at kind of your aptitude for research. They want to see how likely are you to succeed. So they want to see that you've done the coursework that you need to do. They don't want you to, they want to know that when you come here, you're going to be able to like complete all your classes, pass all your classes. And then they also want to know that you're going to be able to do research and produce research output. And if you've done that in other fields, chances are it's going to transfer and you can also do it in the new field as well. And I know several students in my program who started off, actually there's one student that I'm thinking of. He came in as a particle physics experimentalist, and now he's decided that he wants to do quantum computing, and he switched fields. So people do things like this all the time. Sometimes you also have people come in and they want to do it. They say they want to do quantum computing and they change their mind and they do condensed matter physics or something. Like all kinds of crazy things can happen. Okay. Can you identify what kind of stuff are inside those racks? Yeah, so the types of things that we have in the racks, one is arbitrary waveform generators. So this is how we can generate arbitrary pulse shapes for basically any like voltage / current shape that you want. And usually we have some sort of like envelope like this, which is a cosine or like a Gaussian or something like this. And then we have these things called Roden-Schwarzes, which are basically just microwave sources. And these generate just an oscillating signal at microwave frequency. And then we have we basically have these IQ mixers, which take the pulse shapes, pulse envelopes, and then the microwave frequencies and combine them together. So then you get a thing that has the microwave frequency contained in the envelope. And then we send that down into the fridge. And we also have kind of the opposite situation for readout. So we kind of take the input from the fridge and the right tone and kind of unmix it to extract the readout signal. Okay. Oh, and then we also have DC control lines, or like a DC current source, so not oscillating. And we use that for static magnetic fields, or like magnetic field pulses to control the qubits. And when I talk about using magnetic fields to control the qubits, usually what I'm talking about is we have the 0 and 1 energy levels, they have some spacing. And depending on the magnetic field that you apply to the qubit, you can make this more or less. So that can be really helpful if you want to move your qubit frequencies around. The other thing is that qubits at different frequencies do not interact with each other. So if you have two qubits and they're capacitively coupled to each other, but they're at different frequencies, far apart frequencies, it's like they don't see each other at all. They can't interact. In the same way that we need to communicate with the qubit at the right frequency, the qubits can only communicate with each other when they're at the same frequency as each other. So a lot of times what we do is we keep the qubits detuned from each other, so far apart in frequency. And then when we want them to interact, we bring them to the same frequency, and then they can exchange energy with each other. And we do that by applying magnetic fields. And just to be clear, the way that we apply magnetic fields is we have a current source. So we are just running current through a wire, and then we run the wire alongside our qubit, and currents create magnetic fields. So I don't know if this would have come up in high school, but maybe you may have seen this, but yeah, like current flowing through a wire creates magnetic fields, and that's what we use. Okay, I'm not sure what the time situation is because I know there's also a lecture. I'm happy.
We can stay on for 2 or 3 more minutes if you want to keep answering questions, Cora. And if you have to hop, we're already a little over time, so that's totally up to you. But yeah, we have a couple more minutes if there's any more questions you want to answer. We can wrap up.
Okay, I'm just opening the chat now. I'm not sure if there's any other questions in here. I think I've covered a lot of this stuff. Oh yeah, how do the amplitude versus phase versus frequency of pulses affect the state of the qubit? This is a great question. So I said that we control the qubit states by applying microwave pulses. These are just like a pulse envelope with that oscillates with the microwave frequency on the inside. And the amplitude kind of controls how much you change the qubit state. So for instance, if you do a weak pulse, you might not like drive the qubit that far from the 0 state, but if you do like the exact right amplitude, you can pulse it down to the 1 state, or from the 1 state pulse it to the 0 state. But you could also do something in between, so you could intentionally do like half the amplitude of a pi pulse to go to the equator. And then the frequency is really important. We need to drive the qubit at the qubit's natural frequency. And if you can also drive it like near to the frequency. And basically what would happen then is normally if you're driving directly at the qubit frequency, your qubit is doing these Rabi oscillations going from 0 to 1, 0 to 1, rotating around the Bloch sphere. But now if you were to drive off resonant, so close to the qubit frequency, but not quite, it will still oscillate. But now it's not going to trace out a full circle. It's going to trace like a part of the circle. So maybe it'll go down like part way and come back up, part way and come back up. So the frequency of the Rabi oscillations are actually going to get faster because the qubit is moving less distance, but you're not getting all the way down to the 1 state. And then the phase is also important because normally how we do it, it would be an X gate. So when I'm talking about pulsing from 0 to 1, that's usually an X gate. But if you shift the phase of your pulses, you can actually apply a Y gate. Okay.
Awesome. I think just because we're a little over time, we can go ahead and wrap it up there. Cora, that was so lovely. It was so amazing to see the labs and also just to have you answer those questions. And from what I can see in the chat and the Q&A, folks are really, really appreciating it. I know we did not get to everyone's questions, but we are going to download those questions and see if we can answer some of those unanswered questions in like a not live format. So we'll keep you guys updated on that.
Yeah, I'd be happy to answer more questions later. And I also just want to say thank you all so much for coming. I actually had so much fun showing you around my lab and seeing how excited you all are about quantum computing and how excited you are to see all the equipment. Really just reminds me how lucky I am to get to do this every day and get to work with this equipment and stuff.
Incredible. And I'm seeing lots and lots of thank yous in the chat. So amazing. But yes, we will also have the recording of this available. We'll send some follow-up materials, and another huge thank you to Cora for taking some time on a Sunday morning to show us her lab. So thank you so much, Cora. Awesome. All right. And for those who are coming to the lecture, we'll see you very shortly. Go take a stretch break, get some water, do what you need to do. And we'll see you at 12:30. Thanks, y'all.